How do you design a system like Yelp, and what are geospatial databases? So today we're going to talk about an interesting design question that I was personally curious about for a long time, and it also came up recently in discussions I had with people I was coaching recently. So today's question is, how do you design a system like Yelp? And let's have a quick chat about what is Yelp. So Yelp is like this website where you can go and you can find restaurants and points of interest in general. It will show you a map with all the points of interest in your area. It will show you ratings, photos, comments and reviews of all those points of interest. So those could be restaurants and barbershops and all kinds of public places where you can go and visit. So two things I want to bring up before we dive into the interview question itself. I've received a lot of comments on my previous interview question videos, especially on the system design videos. And lots of those comments were very positive, and was really glad to hear them. And some of them were negative, and some of them were negative but very constructive. So I want to address the negative but very constructive feedback I've received. And one point was that my videos don't show how to solve the problem, meaning I did a lot of research before I created those videos, and the videos did not reflect how you should come up with a solution on the spot, like on the spot problem solving. What I want to say about this, yes, it's true, and I mentioned it in every video. I did research about those topics beforehand, and I combined this research with background knowledge I had from just past experience. For sure, you need on-the-spot problem-solving abilities to succeed in system design interviews, but you also need to have certain knowledge on big system design problems and big system design approaches. So from knowing how certain problems are solved, you can apply those approaches, or at least similar approaches, to other system design questions. So you recognize a certain pattern, you recognize certain problem statements, and you can apply the same patterns from other system design questions and other system designs and system architectures in general. And for today's video, it's going to be the same thing. I did research quite a lot on these topics, and I did learn a lot of stuff myself. And I want to bring that to you. I want to tell you what I learned about those systems, and I want to combine it with, again, background knowledge I had from past experiences. So all that is to say, my videos are not, step-by-step instructions how you should go through this system design question. It's motivation, it's inspiration. Look at them, try to take some things away from them, try to, again, see patterns and try to maybe take away the general approach, the structure that I'm doing in those system design interviews. When it comes to content, the exact questions and the exact topics I discuss, some of them are going to be relevant if you get a similar question, but some of them are not going to be relevant, and you'll have to work with the interviewer and with the person you're discussing those problems with. You have to turn on your brain, you have to work through those interview questions in a dynamic fashion, so they can go into any direction, and you have to follow, and you have to, again, apply this on-the-spot problem solving. Okay, so as always, let's identify a couple of core features before we dive into any solution approach. So core features of Yelp, in my opinion, would be something like a point of interest catalog. So you need to store those points of interest somehow, meaning restaurants, barbershops, cinemas, coffee shops, whatever those POIs are, you have to store them somewhere, and people need the ability to discover and browse through those. Another interesting and very crucial feature, I think, is discovery of those points of interest based on the user's location. So as a user, I want to be able to say, I'm at this point, I'm at this geographical coordinate, and what is around me, in a certain radius of 200, 500 meters, 1 kilometer, what points of interests of a certain category are around me. And then to wrap all those points of interests up, we need to have ratings, comments, and maybe reviews on those points of interests. And if we go one step further, we could also think about uploading media like photos and videos to each and every one of those POIs. Okay, so because we're already talking about the database schema, what we also need is a basic user table, which identifies a user and enables things like authentication. And for the sake of simplicity, let's leave it like that. So we have our catalog, we have categories, we have a couple of columns in this catalog which describe every point of interest. We have a couple of users, and now going back to the application layer, you will need a couple of operations to make on this catalog, right? So maybe we want to allow users to create more points of interest. Maybe we want to allow users to modify certain POIs. So we need, the complete range of CRUD operations. And then we mentioned that we want to have ratings and comments on those POIs. So what you want for ratings is a log of every rating that a user gave to a POI. So that's going to be a separate table where you could store a user ID, a POI, primary key, so to say, and a rating. They will give you a big table with a lot of interaction, which is quite write heavy. Also an interesting thought here. The user table will probably be less write heavy. The ratings table is probably very write heavy. Then there will be a review or a comment table, however we want to call this feature. That will possibly also be a little bit write heavy, but I would assume that people give more ratings and comment less. And then for media, we would have a media table which would do the same thing, right? We would have a media ID, so to say, pointing to a user and pointing to a POI. And the photo or video itself would probably be stored in some sort of a blob storage. And that could be something like S3 or some sort of storage layer that is specialized on static content, so to say. Okay, so now we have the ability to upload comments and ratings and photos. Your application layer will have to support all those operations. So when you draw this on a whiteboard, you will have this application layer in the middle of this app and storage layer, and this will be worked on quite heavily. So it will change quite heavily whenever you add new features and new functionality. Okay, so now let's talk about the very interesting feature here, the one key feature that made services like Yelp so successful. We want to have this geographical context, and we want to be able to say these are points of interest in your proximity, right? These are problems which are outside of the realm of just having a catalog which you can browse through. So we have to think about how to store geographical information of those POIs in a database, and how do we easily query those POIs and their geographical information. Okay, so this by itself can be a huge topic, and you wanna again start with a single use case which you can dissect and disambiguate, and from there you can dive into more detail. But let's assume all we care about is the simple use case of opening up this app, the user being at a certain location in a city, let's say, and then we want to show in a 500-meter radius all the points of interest which are around that user. Okay, so how do we do this? How do we store geographical information about a POI in the database, and how do we put this geographical information in relation to the user's location? So a naive solution approach would be to store latitude and longitude in a database. So we could have a column for latitude and a column for longitude for every POI, right? So that's going to be a floating point number, which we can use to very precisely pinpoint every POI on the map, you know. So we can uniquely identify every POI on the whole world. Okay, so now we have latitude and longitude for every POI, and we can get the same for a user. So the user's device, like the user's phone, will give us the latitude and longitude for the user itself. And this naive solution would then go ahead and compare that information, you know, the user's latitude and longitude, with whatever we have in the database. So we could say, you know, given a certain range, make a query in the database where latitude is between values xi and xj, and longitude would be between yi and yj, so to say. Okay, so we will make a range query in the database which scans this whole POI table, and it picks only those POIs which match those two criteria we just defined. Okay, so what is the problem with this approach? Why is it a naive solution? You heard me saying the word scan. So meaning we have to scan this table and we have to make this range query, which the database engine has to go through every row we have and compare those values against those criteria. And a POI table with all the restaurants in the world can get quite large. Even a POI table for a single city can get really large. So even if we do something like geographical sharding, so vertically, you know, separating those database tables, it's going to be a big table to query for. Okay, so what does it mean? Scanning a big table will be very expensive and will be very slow. Not a good customer experience. How can we do it better? So what we have to understand before we go into the better solution of this, databases, you know, Postgres, MySQL, all those databases which are used for common purposes like, I don't know, e-commerce websites, for example. They are optimized to make queries with indexes, and those indexes are very good at looking up string values, for example, right? So you can do very fast lookups on just strings. But those floating point numbers we use to identify, you know, geographic locations are a different beast. So database indexes are not going to be helping us in this case. And this is where so-called geospatial databases come into play, and other solution approaches we're going to discuss now. Okay, so there are geospatial databases, and let's remind ourselves what's the goal here. So what we want to do is we want to make a simple query which gives us all the POIs in a given range. So again, let's say 500 meters. And we want to make this query as simple as possible. So we should be able to make a query with just, you know, one string querying one column. So what is a geospatial database? So essentially those are databases which come with the properties that you're looking for to solve such problems. You know, every time you have geographical information, you know, whatever it may be, something like Yelp or something like Uber, you know, they optimize indexing. So they give you so-called geospatial indexes, which allow you to make queries, you know, like proximity queries or distance queries, or, you know, shape queries to find the shape of a certain object in the world. They're optimized for those kind of operations because they have those geospatial indexes. And how those geospatial indexes work, to my understanding, those are so-called R trees. So you know, they split the world into a lot of rectangles, and they do some sort of an n-ary search on those rectangles, splitting up the world. But today I want to discuss a very interesting approach, something that I didn't know before easily, and we can explain it here, and it's a quite interesting concept. So the concept I'm talking about is called geohashing. So what is a geohash? Okay, so a geohash is, like you can imagine, a hash, so a couple of characters and numbers, so just a string, right? Which defines an area on the world map, so to say. So the whole world is divided into rectangles of a standardized size, and there are a couple of big rectangles. If you imagine a world map with one character, so A, B, C, D, 8, 9, 1, 2, 3, something like this. I think actually 1 is not part of it, but let's assume, I think if I remember correctly, 9 was used for part of the US. So it's just one character, right? This one character defines a rectangle which is on the map of the world. Okay, now so we have a grid which defines the whole world map, and it's a base 32 grid, right? So we have 26 characters and numbers. Not necessarily though. We can also use integer-based identifiers for each grid, and that's details. But just saying, you're not bound to this base 32 grid. Now every grid, so let's say there is grid 9, which defines parts of the US, is divided again by multiple smaller grids, and again they have a certain size, and now these smaller grids in grid 9, they will have one more character, so let's say 9C, right? So then you dive deeper into this 9C grid rectangle, and this is what the geohashing folks call telescoping. So you're zooming into 9C. So then 9C is then again split into a smaller grid and a smaller grid, and every time you add one character to it, right? So at some point you'll have something like 9C, 2, 3, A, B, whatever, and you end up with a very precise location on the map, which is unique, right? This hash, this string we just created by zooming into this one grid is unique across the whole world. And you can remove a character and it will zoom out of the map. You remove another character and it will zoom out again. So depending on how much level of detail you need, you just take away characters and it's like zooming out of the world map. And now let's talk about why this property of geohashes and arbitrarily taking away characters is so beneficial for this use case. Okay, now we know how geohashes work, and let's circle back to what we actually wanted to achieve. What were the properties we were looking for? We wanted to have a string in a column which we could easily index and then do quick lookups. So geohashes give us exactly that, right? Instead of defining a certain region on the map by two columns which contain floating point numbers, we have one column which we give a certain hash length, so let's say 9 characters, and that pinpoints this POI on the map very precisely. So that's one property we were looking for. Then how do we implement this proximity feature, right? So we had a certain coordinate on the map, and we wanted to know what is around this coordinate, what kind of POIs are around it. So something really easy we could do, I'm sure it's not the perfect solution yet, but it's better than the naive solution. You can have a certain column for every POI, which is, let's say, 6 characters of the geohash. And those 6 characters will put every POI in a grid on the world map, right? So then when we have a user's location, we transform this user's location to a geohash itself, and then we can query all grids, so all geohash grids, which are, let's say, those 6 characters minus 1. Okay, so this will give us all POIs which are in a couple of grids around this one coordinate. And if you want to have a bigger radius, we would take those 6 characters and do a -2, which will give us a bigger radius. So you will need to store every POI, so you need to store a column for every POI with 6 characters, and then you could do denormalization where you also store a column with 5 and maybe 4 characters. So now you have 3 geohashes for every POI. That's certainly not optimal, because you need a column where you potentially store redundant information, but it will allow you to index those columns because they're just arbitrary strings, so to say, and you can do very fast lookups based on I want to know every POI which has this one geohash. So I've read that there are more optimized approaches which use geohashes with integer ranges instead of base 32 encodings, but I'll leave it up to you to read into that more. I think we arrived at a fairly good solution where we learned about a new system to rasterize the world, and geohashes have very nice properties we can use for all kinds of operations, and proximity being one of them. And let's touch on one little optimization I've mentioned in the beginning. I've mentioned sharding. So what is sharding? When we talk about sharding in the sense of databases, we talk about how can we split up the database into multiple databases or multiple tables or multiple database instances, where by splitting it up vertically, we can optimize for certain properties. So in this case, we would again try to optimize for latency while reading. We can use properties of the business problem, so to say. So in this case, the business problem is that we care about POIs which are in the proximity of a user. So a very straightforward approach would be to shard the database across regions. So you would have one database instance which contains all POIs for the region, let's say North America, and another instance which contains Europe and Asia. That would easily give you smaller tables to query, which could bring down latency whenever a user opens up the app and tries to query for POIs. So this is only one use case where you can apply sharding, but usually it's around this topic, right? So you have a monolithic database, and using properties of your business logic, you try to split it up, and by splitting it up, you try to optimize for some property. Okay, let's do a quick recap. We identified 3 core features. We talked about the approach you can take to talk through certain layers and establish a certain base with your interviewer. We talked about a bit of a database schema, starting off with a very, very simple database schema just to browse a catalog. Then adding a user table, and then adding tables and storage for media like photos and maybe also comments and ratings and this kind of stuff. There are more topics you can dive deeper into, and again it depends on how this discussion goes, in what direction the discussion will go. There is a lot of room for improvement when it comes to media hosting. So from looking at a couple of resources, I know that Yelp uses, or at least used, content delivery networks to bring media content closer to the end user. So content delivery networks again are used to host static content, and knowing that you have a big user base looking at a subset of your data, which is in this case very convenient. You can place this media, you can place this data in a data center, in a content delivery network close to the user, which again optimizes latency and so on. So a lot of topics you can talk about in more detail, and depends on how the interview turns out. And I also want to mention that I'm not an expert on geospatial databases, I'm not an expert on geohashing. I'm going to put all the resources I've used to create this video in the section below, and you can read it up and look at one of the videos I've used to research this. It's super interesting, and it explains an approach where they compared R trees and existing solutions in, I think, Postgres and the PostGIS geospatial database with a self-grown solution. They compare latencies of lookups for a very similar approach. So give it a look. Super interesting video. So I hope this video was helpful for you. I certainly learned a lot from making it. It's a bit of a niche topic, but if you think about all the apps and all the services you use which are based on geographical information, it's actually quite a broad topic and very relevant in modern times. So I hope you can take away some learnings here. Leave all the questions and comments you have in the comment section below. I'll try to answer what I can. My name is Ramon Lopez, and this is Success in Tech.